Today I'm going to take you on a fairly speedy tour through some of the artificial intelligence research that's been happening at Edinburgh, and I've decided to base it in one of our centres for doctoral training, which I hope will delight EPSERC. The students have been exceptional. They are one of the biggest bits of the workforce for us in terms of doing cutting-edge research, and they've been publishing some tremendous papers. So I'm just going to kick off by showing you what I think of as perhaps the big landscape here. And we probably focus an awful lot in our research and in the sort of the emerging research in this area down here, where we're doing lots of molecular or maybe text-based analyses or image-based analyses. But in fact, in biomedical AI and health AI, it's probably this top left corner here where we're talking about things that some of us might think are perhaps less exciting, but in fact actually have much greater immediate impact in the health service. So things like provisioning hospitals, making resource decisions. And there's some tremendous examples in Scotland of this in practice in various of the NHS trusts. But today my talk is largely going to be focused down here, but very happy to talk later about some of these other things. I shouldn't ignore what has already been mentioned, is that there is a huge overlap with lots of very important components that aren't strictly necessarily just about the methods that we use, but about the impact that they have on society and the problems that they engender. Also the impact that these have in society, especially when we're working with people's data and with such an important outcome as their health and well-being. So this is not ordinary machine learning or AI. We're operating in a very protected and special space, and we need to keep that at the top of our minds. So first thing I'm going to just talk about very briefly is a paper that came out from these three research students from the CDT, which was looking at how you tackle the big problem of harmonization of data, really. So this is a massive problem in the health service. So how do we actually bring very important data sets together so that we can jointly analyze them? We're getting larger and larger cohort data, many different modes of data. How can we be confident that when we integrate these things together, we're not introducing very important systematic biases? So this paper looked at a rather interesting and nice way of trying to sort of align a long-standing data set that we have here in Edinburgh, the Lothian birth cohort, with Generation Scotland, another Edinburgh-located project, where we've done, the university has done long-scale monitoring of large cohorts. And in this particular paper, they used DNA methylation as a proxy to measure how well these things can be integrated and the effect that different methods of integration can have. And while this might seem like something that's a bit of data processing, this actually determines pretty much the quality of what comes downstream of here. So it's really important that we understand that data harmonization and standardization is an absolutely essential first step. We need to understand how that works and be confident that what we're doing is sensible. So we're going to hear, I think, perhaps a bit about protein design later. This is a project from Leo Castorina in the CDT that actually uses generative models to try to predict new sequences to predict protein structural space. So one of the key design decisions that people want to do when they want to try and match molecules to surfaces is the shape, the architecture of the backbone that goes into, for example, a binding groove. And there are lots of methods to do this. This particular method uses a very clever way of sampling that new space by treating the protein structure as what's called a voxel model. So it makes a 3D landscape of the protein, and then it uses the features of the parts of the protein in that particular part of the map to learn about its properties. And this system allows you to generate novel sequences which should fold to form the structure that you're looking for. And so in this project, they use AlphaFold to predict the structure made by their novel sequence and then measure how far away it was from the original protein sequence they were trying to generate. And it turns out this particular model is state-of-the-art at the moment in that process. So this is quite an exciting project. So a lot of you will be hearing about sensors. So here we have a wearable device. This is an E4, a bit like a very powered-up Apple Watch. And it can measure a bunch of physiological data from patients passively in real time. So in this project, Filippo and Brian took data from a prospective study looking at several hundred patients with mood disorders and took the telemetry data from this watch and used it to do multi-class prediction on their mental health state. And this is quite a novel approach, because often what these methods do is simply detect whether someone has a mental health problem or not. This actually maps the physiological data here to the individual assessment criteria on the standard tests used for mental health evaluation. So this is transformative because instead of simply saying someone has a mental health problem or not, you can actually specify what the likely clinical profile of that is. And this is being rolled out in practice. We have another one here, which is looking at metabolite data. So looking at whether we can integrate data from large cohort studies, looking at the association between particular sort of phenotypes. So things in this case, they're looking at fatty acids measured in people's blood. And then they're looking at the genetic association that underpins it. And in this study, they show a causal relationship between fatty acids and mood disorders again. So I think what you should be picking up at this point is integrating lots of different kinds of data to make really actionable predictive outcomes in real life. Here's another example, which is an image-based one. Again, this is another thing where the state of the art here in ophthalmology would be to take some kind of OCT or a wide field image and classify whether the patient has an eye disease or not. Again, in this case, the student has trained a model which does multi-disease, multi-class prediction. So here it can predict any of 7 different eye disorders with very, very high efficiency. And several interesting things emerged from this, one of which was that it's always been thought that you need to use these ultra-wide field, very big, quite expensive machines to get this data. This study shows that, in fact, you don't need the peripheral information in these images to make accurate diagnoses. So that could have big impacts for countries, especially that can't afford expensive scanning equipment. Probably running a little short on time, but I will keep going for a while. So another one is back in the molecular sphere. We can use multimodal data sources like this, and we can map them at the patient level to look at how similar patients' profiles are for some of these different genomic data modalities. And we can use network approaches to integrate these and then use graph neural networks to make predictions about patient status. So when you do these kinds of studies using this kind of network fusion approach, we find that we can retain many, many more patients in the study. We don't lose them because of missing data, because of this method allows us to learn from patients that are very similar to each other. And that has also been used in a Parkinson's study where we look at the progression of Parkinsonian state across time. We can use these integrated models again to make predictions at different time points of what the likelihood is of a patient going on to progress to the condition. And again, all of these are sort of novel approaches to use integrated multimodal data for predictive purposes. And so this is happening across the world, but a lot of this is happening right here in Edinburgh. And it wouldn't be a talk of mine without mentioning this quickly. So obviously people know that large language models have got huge potential for impact in biomedicine. 80% of clinical data is unstructured and contains very important information about the patient, the diagnosis, the prognosis, the features of the patient. And so there is a very large biomedical NLP grouping here in Edinburgh that are studying various technical tasks to do with extracting structured information from these data. And finally, slightly further into the future, we're now starting to think about how we can use generative AI models to build digital twins of all kinds of different systems that are relevant to disease. This could be cellular, it could be organ system models, it could be multi-scale models. And now that we have a lot of capability in building complex foundational type models to generate data of different modalities, there are some really nice foundation models, for example, in single cell sequence data, we can begin to stop thinking about just an individual data modality and instead think about how we combine lots of data together and get the best from all that data to use predictive systems like this. And that's probably the best take-home message for today from Florian Markowitz, is that these models can be highly performant in the academic setting. What we really need to now show is how we make those things work in the real world. And that's another very large task to undertake. These are references that people can look up, and it wouldn't be fair for me not to mention this. We are very fortunate to have been awarded a follow-on doctoral training grant, which hopefully will do at least as much and more still in this space. But this one is specifically trying to do what I just talked about, translate novel research into clinical and healthcare practice. So we're trying to put this into the real world. And I think I'll leave it there. Thanks.